Okay, welcome class to the final video lesson for Chapter 7 of the Financial Applications unit. We're going back to present value in this lesson, and this is present value of an annuity. So we know for ordinary simple annuities there are regular payments, regular deposits, regular amounts that are involved at the same frequency as the compounding. And we know that these payments or deposits or amounts are taken at the end of the compounding period. Now, in present value of an annuity, this is a little bit of a different type of an investment. Let's review the formula to calculate the principal for a future amount. So this was going back to our initial look at compound interest, and we recall that we had the amount, which was the future value, coming from the exponential growth of a principal amount. And we want to calculate the principal. We would take our future amount and we would divide it by this growth rate raised to the number of compounding periods. Now this works well if we want to consider how much we need now in order to provide for an amount in the future. But it also works well whenever we have multiple amounts in the future. And so we're going to introduce here at the outset what the present value of an annuity is. So when a principal is invested or borrowed and it earns compound interest throughout its term, and take note, equal withdrawals are taken off that principal at the same frequency of compounding, this constitutes a present value annuity. Some applications would include the provision of a regular income, perhaps for retirement, or the payment of a loan where the principal amount was a borrowed amount or a purchased item that we couldn't pay for outright with cash. So let's consider a situation here to help us frame this present value of an annuity. Consider the need for $100 withdrawals as perhaps income supplements or loan payments every month for 3 months. So we'll just consider a very small period of time here just to help us understand the application. How much money would be needed at time 0 to provide for this $300 amount, given that the initial principal is invested at 6% compounded monthly? So let's consider this introductory scenario here. We need $100 every 3 months. Now, how much would we need to invest now? Well, just by our knowledge of compound interest, we would understand that interest is earned. So we wouldn't need $300 currently, because that's all you'd need to provide for the 3 withdrawals if it was just sitting there in your drawer at home. But if it's earning compound interest at a rate of 6% annually, and it's compounded 12 times a year, even though we're only going to get 3 months into that year, we probably don't need quite $300. So let's just actually consider here, well, what if $300 was placed in the account? Or what if $300 was the borrowed amount, and we're going to take that and pay it back? Okay, so let's consider this. Now, these $100 withdrawals, if these were loan payments, 3 $100 amounts would be paying off a loan that was less than $300, obviously, because if we're paying interest on our borrowed amount, we would be certainly paying more with the payments plus interest than we actually borrowed. So clearly the present value, the amount that would need to be in that account for multiple reasons, is going to be less than $300. Let's assume we'll put $300 in as a start and just see how much we have left over at the end. And what we're going to do is we're going to approach this as we have before, where we're going to look at the opening balance, we're going to look at the compounded amount for that term, and we're going to look at the withdrawal and then the ending balance. Okay, just modify my table there. So we're looking at months. Opening balance is $300, and of course at 6% annually, or annual rate is 6%. I just specifically chose that so that our term rate would be exactly a twelfth of that, which would be 0.005. Okay, so that's our term value, and the frequency here is 12. It's compounded monthly. So in this first month, we've got a $300 amount in there. Now, the withdrawal is not going to happen until the end of the month. So throughout that month, we're earning compound interest at a rate of 6%, 0.005% a month. So at the end of that month, the $300 converts to $301.50 with that 0.5% of interest earned for 1 month. Then the withdrawal occurs, and so our ending balance is $201.50, which opens our second month opening balance. Of course, what's going to happen now is the $201.50 is going to earn that 0.5% for that 1 month, and another $100 withdrawal is going to be made at the end of that second month. To complete the table, the end of the second month, the ending balance is $102.51, opens us up for the beginning of the third month, which again, 1 month of interest compounded brings us to $103.02. $100 comes off at the end of that month, leaving us with an ending balance of $3.02. Now, the only problem with this sort of simulation that I went through here is that the initial opening balance here was clearly more than what was necessary to provide for these equal withdrawals, meaning that it exceeded the loan amount, or it exceeded the amount that would need to be invested to provide for those equal withdrawals. So in a loan situation, we don't want to end up owing anything, which means that our payments, represented here as the $100 amount, have to exactly bring us to a closing loan balance of zero. Another way would be that if this was an investment, the withdrawals exactly deplete the initial investment. So clearly the estimate of $300 was on the high side. Okay. Now this is one way to look at what's happening with the present value questions. And usually students struggle once they've learned future value of an annuity, where you're making regular deposits and it's building up to a future amount. They struggle with understanding present value of an annuity, where you're making a single deposit initially and it's leading to either regular withdrawals, or it's causing, in the case of a loan, regular payments on that borrowed amount. So really what we want to figure out is, how would we calculate this more accurately? How would we calculate what is necessary to produce three $100 amounts, assuming 6% annual rate and monthly compounding and monthly regular withdrawal? So let's look at this a little bit differently using a timeline. So our scenario is $100 regular withdrawal every month for 3 months. So our timeline only needs to go up to 3 months. And this time we're going to represent, we can sort of focus on this part of the timeline. We're going to represent these regular withdrawals using the present value calculation. The present value calculation is the future amount that's needed divided by 1 plus the interest rate for the term raised to the number of compounding periods. Of course, at the end of the 3 months, the amount that would have been needed to provide for that withdrawal would be $100 divided by 1 plus the interest rate raised to the exponent 3 for 3 compounding periods. So if you can picture that, this amount here, whatever amount of money at present, is going to be compounded 3 times to produce $100, and that's how we would calculate that. Now, just for simplicity, I've used interest rate I instead of the 0.5%. So wherever you see I, just imagine that as the 0.005. Okay. Now, the amount that was withdrawn at the end of 2 months, now it didn't have as much time to earn interest, so more money would have been needed in that pot there at the beginning. Now I'm treating these as separate amounts here. You'll notice that. Okay. Finally, the amount that was drawn at the end of the first month would have required the greatest initial principal because it was only compounded once. Okay, so these three amounts collectively, if I were to add them together, these form a sum of a series. And this series, of course, because these amounts are linked by a common ratio, is a geometric series. And you'll see the form of it right here. It's a geometric series where the terms are from smallest to largest in increasing value of money. The first deposit, 100 over 1 plus I cubed. The second, 100 over 1 plus I squared. And the third, 100 over 1 plus I to the 1. Okay, so this is a geometric sequence. Summed would become a geometric series. The first term of that, of course, is the 100 over 1 plus I cubed. The common ratio, and this is a little bit harder to see, but you notice what's happening in the exponent here is that it's decreasing by 1 each time. Now, what would cause that to occur? Well, it means that a factor of 1 plus I is being multiplied to move from term to term in the sequence. Okay, so this, in order to reduce the exponent on the growth rate 1 plus I, we would need a factor of 1 plus I in the numerator. Okay, and so if you can accept that, obviously the number of terms is 3. And so for summing geometric series, we've done this before in chapter 6. It's first term multiplied by common ratio raised to the number of terms, subtract 1, all over common ratio subtract 1. Substituting these values in to the formula, we get something that looks at first a little bit awkward to work with. Okay, there's our A right here. Here's our R, N, subtract 1 all over R, subtract 1. Now I'm going to just modify this a little bit to make it a little bit easier to work with. Where I see 100 over 1 plus I cubed, I'm going to treat that as 100 times 1 over 1 plus I cubed. That's equivalent. Should be able to see that. And of course the reciprocal of 1 plus I cubed is equivalent to 1 plus I to the negative 3. This is an exponent law that you may have seen previously. For example, 4 to the negative 1 is equivalent to 1 over 4 to the 1, and say 4 to the negative 3 is equivalent to 1 over 4 cubed. So I'm doing that because I want to bring the growth rate raised to n up into the numerator. And at that point, I've got something a little bit more workable. I'm going to take my numerator, multiply it out again. What I'm doing here is I'm just multiplying the 100 staying as a factor, and this term that I've brought up with a negative exponent is going to be distributed through the square brackets. Now take note, exponent on this growth rate is negative 3. This is an exponent of positive 3. And you multiply two powers with the exact same base. We do what? We add the exponents. Negative 3 plus positive 3 is 0. So we really have something raised to the 0, which of course is 1. The second part of the distribution would be multiplying that growth rate raised to the negative 3 by 1, and that's subtracted from the first term of the product. So we're going to get two terms in the square brackets. One will be the first term, and the second term will be 1 plus I to the negative n. All over in the denominator works out much simpler for us. It's 1 plus I subtract 1 would give us simply I. Okay, and there of course is the form for the sum of this geometric series. Now we could compute the value of this sum to figure out, in this case, of course this is not n, this is actually 3 down here. So let me just correct that. And we have numerically everything we need to solve for this, recalling that I was 0.05. So at this point, with some steps and maybe double checking your calculation, with the substitution of the term interest rate and everything else being equal, $297.02 would be the present value of this annuity, meaning, going back to our timeline, the sum of these individual investments would be $297.02. That would produce the three $100 withdrawals. Going back to our table, $297.02 would be the actual amount that is needed to provide for these three $100 withdrawals. So you don't need as much money as you're going to withdraw, obviously, when you're earning compound interest. But thinking of it another way, you make more of a payment on a loan than what you actually borrowed, which of course is the price for borrowing the money, okay, or the item purchased. So this is present value of an annuity. The example in your textbook works with a $1,000 amount playing out over 20 years monthly, which would involve 240 compounding periods. The timeline for that would certainly be a much bigger monster to draw, but a simple timeline can illustrate what is happening here for a general investment of some initial present value with some general withdrawal amount R, being the regular withdrawal, over some general length of time N here. So if we can accept these generalities here, the regular withdrawal is 100 in our example. Now we're just using R. And in this timeline, N compounding periods later, withdrawal of R is made, and that had N compounding periods to accumulate interest at a rate of I. So the principal needed to provide for this withdrawal would be this much. The principal needed to provide for this would be this much. It had one less compounding periods to earn interest, moving all the way back to the second withdrawal that was made, which could only have 2 compounding periods of interest time. And finally, the first withdrawal that was made only had 1 compounding period to earn interest. The sum of all these is, of course, the present value that was needed at time 0. This, of course, again, is a geometric series, and generically is shown there with all the terms added up. Of course, the first term can be seen right here. And the common ratio, again, is still little r here, 1 plus I. Everything else is the same. Number of terms is n. So this substituted into our formula shows generically what we get when we don't use specific values. Notice here the adjustment to the first term. The denominator is brought up with negative exponent. Distributive property plays out, and we get our formula for the present value of an annuity, which we generally call PV. Okay, and here it is right here. Present value is R, 1 subtract 1 plus I to the negative n all over I. This, of course, can be used, again, when the payment interval is the same as the compounding period, and the payment is made at the end of each compounding period. The first payment is also made at the end of the first compounding period. So at this point, I'm just going to go through the steps to solve for the common ratio, or sorry, the regular payment, capital R, from the present value. Pretty straightforward. The input-output diagram only has 2 main steps here. We're starting with the regular payment. We have to do some work in the square brackets, but that's all separate depending on the number of compounding periods and the interest rate. And then after that, we divide by the interest rate, and that gives us the present value. If we have the present value and we want to find the regular payment or the regular withdrawal, we simply reverse our steps. We would multiply by the interest rate and then divide by the value shown in the square brackets. Okay, at this point, I've explained all that I really want to with respect to the meaning of present value, and I think the examples are sufficient to illustrate the concept, and the idea of the timeline is really key here. The main difference, of course, with present value is it's a single deposit made at present, and it plays out over time, creating regular withdrawals. Eventually, at the end of a present value of an annuity question, you've got no money left, which means you've either drawn out all that can be drawn from the initial principal, or you have paid off all that needs to be paid on the original balance owing. Unlike a future value of an annuity where you're starting out with 0, no money, and you're accumulating to a great amount in the future because of regular deposits. This is the main difference between them. Of course, the applications, there can be a little bit of overlap. Investments can be involved in both. I'm going to just close this video off at this point. I'm going to include a second part to it, which goes through some examples, which you can certainly read from the textbook as well. And I'm also going to go through the investigate on pages 456, 457. So look for part 2 of this video lesson, and you have your worksheet. At some point, you'll want to work through many of these questions so you become comfortable with how to solve for the present value or the regular deposit, rather regular withdrawal, and also being able to distinguish between a future value and a present value of an annuity. Take care.